dia a todos. Hoje eu queria apresentar o Emilio Zanatta, que fez o doutorado na Universidade Federal do Rio Grande do Sul, com a NSCs. Eu estive na banca dele e achei muito impressionante como é que ele achava os aglomerados globulares no meio de distantes em galáxias diferentes. Um trabalho de redução de dados assim horrível. Então ele faz uma coisa que nos interessa muito, porque aqui no nosso grupo a gente trabalha com aglomerados da galáxia, ele trabalha com aglomerados de extragalácticos. Então, Emílio.
Obrigado. So I'll present in English. Thanks for the opportunity to present here at USP. Thanks to Beatriz for the introduction. So today I'll talk about nuclear star clusters, and specifically the role of environment in their formation and evolution. And this is a work that is a two-part work, and the latest part of this work was just published this month, and it's available on archive. I strongly suggest you, if you are interested in what I present today, to check after the presentation. So I'll start by talking about what is a nuclear star cluster. So a nuclear star cluster is essentially, at first glance, a very large globular cluster. But it is located at the nuclei of galaxies of very different, of every morphology and size that you can think of. And they are generally found by the fact that there is an excess in surface brightness at the center of galaxies. But it is the nuclear star cluster is much more important for the evolution of dwarf galaxies, if you think of it. It's very easy to see why. First, because here's an example of a dwarf galaxy with a nuclear star cluster at the center, and you can see how much of it the nuclear star cluster takes of the whole brightness of the galaxy. In an image like this of a galaxy cluster, you can see, this is from the Coma Cluster, you can select any patch of the image and you find several dwarf galaxies with nuclear star clusters within them. And I just want to point out that this is just a matter of contrast. This is not such a large nuclear star cluster, but nuclear star clusters vary wildly in brightness too. So a few very maybe more familiar objects for you are Omega Cen and 47 Tucanae, which are globular clusters from the Milky Way, the largest ones. And they are regarded as most likely were in the past nuclear star clusters of dwarf galaxies that the Milky Way might have accreted in its past evolution. So if you want to see what a nuclear star cluster looks like up close, these are good examples, although they are probably more dissipated along time. So why study nuclear star clusters? Well, it's a bit biased by my research, but the first thing I would say is that they are very important to dwarf galaxy evolution, but they are also important because, as I said, as they are located in galaxies of any different sizes, and always at the center, they can tell you a lot about how do the star formation works at the center of galaxies in such a extreme environment with so much gas and a lot of stuff, as you can see in this figure here at the bottom right. Also, as you'll see shortly, the evolution of nuclear star clusters is very tightly correlated to the evolution of globular clusters. As I just said, they can be used to understand the properties of nuclear star clusters. We can find the evidence of merger remnants, such as Omega Cen and 47 Tucanae. And of course, we can know more about the host galaxy evolution by studying nuclear star clusters, and so on. Now I want to talk a little bit about the formation and growth of nuclear star clusters. First, I think it's important to point that we don't know very exactly whether or not it's more common for the nuclear star clusters to form before the galaxy forms or after the galaxy forms. So it's kind of like the chicken and egg situation. Because like the nuclear star cluster is such an important part of galaxies with low mass, And in galaxies that are more massive, it maybe start small and get bigger over time, but still maybe formed in the early moments of galaxy formation. But there are two main theories of the growth and the formation and the growth of nuclear star clusters. The first one, which is considered to be the dominant form of nuclear star clusters to form, is the GC in spiral theory. It's basically the effects of dynamical friction that over time globular clusters formed elsewhere around the galaxy spiral towards the center of the galaxy and then merge into a big star cluster at the center. It is supported by several simulations. The fact that there is a high specific frequency of globular clusters in low massive nucleated galaxies, and the fact that there is a deficit in massive globular clusters in early type centers, which means that those massive globular clusters might have come to become the nuclear star clusters over time. The other formation theory that is not excluded between the two, they might happen at the same time, but in a lesser extent, is the in situ star formation, where gas spirals toward the center of the galaxy and forms the stars there into a large cluster. This is supported especially by the young populations found in all close nuclear star clusters in the vicinity of the Milky Way, the rotation and flattening of NSCs in this region too, and there is an evidence for a transition at 10 to the 9 solar masses when you see the fraction of nucleated galaxies, as I will show very close to. So now I'll talk about the environment, which is where my work resides in. So the environment and its relation to nuclear star clusters have been studied for a long time, since the 80s. However, it only took off really in the 2010s, almost 2020, by the work of Sanchez-Janssen in 2019, which showed that compared the nucleation fraction, which is simply the number of nuclei over the number of galaxies in a given environment, he compared this nucleation fraction in Virgo, Fornax, and galaxies in the vicinity of the Milky Way and the Milky Way itself with the nucleation fraction for Coma galaxies in the work by Den Brock et al. 2014. The Brock et al. Work only had this mass range of the galaxies in Coma, so we lacked a few information in the low mass ends. However, you can already see that it suggested very clearly that there might be an increase in nucleation for a fixed galaxy mass in some environments compared to the others. And this motivated our first idea to do this work in a paper that we published in 2021. It was exactly to fill this part of this plot with the low mass end of the Coma environment in order to testify if really there was an increase in nucleation in one environment compared to the other. So we can say that the environment is another part that can be studied using nuclear star clusters. So as I said, our work then would compare the galaxy nucleation in different environments from groups to clusters. We used a lot of literature data to do this work. For instance, the Virgo cluster data from Sanchez-Janssen in 2019, the Fornax cluster nucleation data from both Munoz 15 and Su et al. 2022, and local volume groups, specifically dwarf satellites of those local volume groups from Kalsten et al. And Hoyer et al. From several different galaxies in the when I say local volume in this presentation, I'm always referring to a region within 12 megaparsecs of the Milky Way. And in 2021, we added data for the Coma cluster, and very recently, we added nucleation data for galaxies in the Shapley Supercluster. But this is a bit of a spoiler. I'll show more about this later. So now talking a little bit of the environment, the new environments that we included, and why did we do that? So first, the Coma cluster, I already explained more or less why we did that. but also because we had access to AGST data, very deep AGST data, deeper than the data from the Brock. So we were able to go a bit further than the work that they did before. It was centering in these two fields around the two BCGs on the Coma Cluster. But later, we found that it was very interesting to look into the Shapley Supercluster. First, because the Shapley Supercluster is by far the largest concentration of mass in the nearby universe. It is have no comparison to other clusters in that are close to the Milky Way, just Coma or Hydra Centaurus. And it is a perfect laboratory to study this kind of, any kind of stellar and galaxy evolution under extreme environment influence. So we looked into the Shapley Supercluster specifically into, because it is a supercluster, so it has galaxy clusters within it. And we looked into mainly the central cluster of Shapley, which is Abell 3558, which has an astounding number of 160 galaxies per megaparsec square. And we also looked into the northwards cluster of Shapley, which is Abell 1736, specifically its lower subcomponent, with 1736A, which has a density, galaxy density of 31 galaxies per megaparsec square. So this was the follow-up from the Coma study. And we had also AGST data for Shapley, which comprised 6 fields in these two clusters with very deep data, which was necessary because of the distance of Shapley, which is over 200 megaparsecs away from us. And yeah, that's basically it. But of course, I'll talk more about this work. Now I want to briefly talk about part of our work, which is exactly to detect those nuclear star clusters in these images. So first I want to say that, as I said in the beginning, nuclear star clusters can be found in galaxies of any morphology. However, there is a distinct difficulty in detecting nuclear star clusters in galaxies that are dwarf galaxies like these two, or big galaxies like this one here. This is mainly because in galaxies like in dwarf galaxies, the nuclear star clusters is very easily detectable because there's nothing on top of it except for the low density of the halo of a dwarf galaxy. While, of course, if you look into a big galaxy like this one, it's very hard to disentangle the bulge and sometimes an embedded disk and other components that are in the center of large galaxies. So this is why in most of the nucleation studies, which have large samples, we only look at the low mass end of galaxy mass and luminosities to get a more reliable sample of nucleation, in spite of the fact that the nucleation, of course, spans much more than dwarf galaxies. But this is not to say that it is impossible to look into the nuclei of galaxies like this one. This is the work from Hoyer et al. 2013 for exactly this galaxy, and they managed to find and measure the nuclear star cluster in it. However, they needed AGST and JWST data to go into the infrared to see really the nuclear star cluster. So it is more a work for individual galaxies, not a whole sample of galaxies like we do in this work. So in our work, we focus on dwarf galaxies mainly. But the definition of what is a dwarf galaxy is a bit depends on what area you are from. But basically, we're going at about 10 to the 9 solar masses of a galaxy. So I'm just showing this image again to show exactly the abundance of galaxies, of dwarf galaxies that we can find with nuclear star clusters. And of course, you can imagine how easier it is to do a large-scale analysis with dwarfs than it is with other galaxies. But of course, I would like to expand this in the future. So dwarf ellipticals this is what's called a dwarf elliptical galaxy, even though this one is a bit more elongated. These are two dwarf ellipticals, are the best galaxies to do this kind of study. They have a reliable NSC detection. They offer a high sample size. However, they are very hard to find. So we had to develop a way to detect those galaxies more efficiently. The way that we did it was simply an interactive process where we start by an original image like this. Then we model each of the large galaxies on the image that might obfuscate the smaller dwarfs in the image. And we get an image like this one with all the large galaxies subtracted. And here I'm showing a specific patch of this image where you can see with a lot of effort, a small smudge, which, believe me, it's a galaxy. It's a dwarf galaxy right here. But as you can see, even after we remove the galaxies, it's still very hard to detect this galaxy, even using something like source extractor or visually. So to actually be able to more efficiently detect those objects, we use source extractor, which is a photometry detection software very popular in extragalactic astronomy, to detect all the point sources in this image. So things like intracluster globular clusters, etc. With that, we are able to get a background image from all the rest in the image that is a smoother representation of the original image. And you can see now that on that patch, we see a much more high signal to noise to that smudge that we saw in the beginning. So now it's much easier to see that that object, in fact, is an extended object and not something from the noise and such.
How do you look at this is a galaxy from globular?
Well, I'll show very shortly how we do that. Because in the end, we model every galaxy using GalFit, which is a 2D surface brightness modeling software. We model the galaxy as a Sesky profile and the nuclear cluster if there is there with a PSF profile. And therefore, it's very, very hard to see like a galaxy like this one and to think that it might be a globular cluster in the end. Because globular cluster at that distance look much more like point sources.
Clear that object galaxies. But when you go to the keep magnitude around say 10G absolute magnitude around times 11, for example, it's very difficult that to say ultra-compact dwarf strong global.
Yeah, but the distance. Yeah, but oh, okay. So the
I'm
question
sorry,
is.
could you please repeat the question?
Okay, now I will just say briefly what the question was. So the question was, how can I, let me go back here. How can I can say for certain that this is a galaxy and not a globular cluster, for instance? I mean, I'm not showing here, but in the paper there is, if you want to take a look. We use the fact that due to the distance involved, we can do a plot like with the effective radii and the surface brightness to see if those objects are compatible with what to expect to be for a galaxy and not a point source. But I also want to say that if you look closely, let me see here. So see this point right here, more or less, there are 2 points here. This is what a globular cluster looks like at this distance. So the galaxy of this size will never be a globular cluster. And this is the faintest galaxy that we can observe in these images. Anyway, so it's very hard to confound any of the two at this distance. But of course, if you look at the forks or the nearby objects, you have to be more careful. So now go, as I said, after we detect all of the galaxies in the image, we use GalFit to model all of those galaxies. So this is a brief rundown of our modeling process. We have the original images of the galaxies here. Then we have here the inverted color images of the background detections. Here we have the point sources masked, and the model with Gauss fit for each of those galaxies and the residuals at the end. So in the end, we had a final catalog that was within minus 7.5 in the I band, the absolute magnitude in the I band, and minus 19 for 66 galaxies in the Coma Cluster, in which half were nucleated. And for Shapley, we had 108 galaxies in Abell 3558, in which 104 were nucleated, and 44 and 16 nucleated for Abell 1736A. Excuse me. Now I want to talk a little bit about the statistical part of our work, which is a part that I like very much. So we had the option when we are doing like occupational statistics to use what is more commonly seen in the literature, is to use beams and connect the dots to see the overall behavior of the thing that we are studying. In this case, the nucleation fraction. But our choice in this work was to use the logistic regression, which is a way to model this nucleation fraction with a more continuous and smoothed representation of the data. And I'm showing here exactly the same data for these two in these two panels. And you can see very clearly that in the right panel, you see it's more easier to see the overall structure and behavior of the nucleation fraction over the range that we are studying. While with binning, sometimes we tend to look into local variations of the quantity we are studying, which may be due to sample size and not exactly physical meaning. So to briefly explain what is the logistic regression, which is a part of what is called a generalized linear model, which is basically a way to get something that a distribution of probabilities that is not linear, as normally we deal with, but linearize it in a way that you can fit its parameters with the common methods that we regularly use. So basically, we model our distribution of nucleation as a Bernoulli distribution, which is a distribution that deals with binary data, such as yes or no, with or without, 1 or 0, or in our case, nucleated or non-nucleated. In that small table, I'm showing an example of the data that we input into the model, which has on one column the absolute magnitudes in the I band, and the other one a flag whether or not the galaxy is nucleated or not. Then what we want in the end is to have the model in this form right here. Something that is similar to the equation of a line, which is a plus bx. And so in the statistical jargon, it's called the beta 1 plus beta 2 times the descriptive variable, which is in our case the magnitude in the I band. We do this by using something called a link function, which is generally denoted as eta, which is basically depends on the distribution that you are working with. In our case of the Bernoulli distribution, this is the logit function, which is just the log of the inverse of the probabilities of the Bernoulli distribution. And so it's basically it. If you model like this, you can use now, you can now fit the betas in this form right here, and then return to the probabilities here. So find the probability of nucleation, which is what we want in the end. So this is the results from our works. First, on the left here, we have the results for Coma in Zanatta 21, that we can see in orange points the regular binning of the data and the logistic regression below it. And an interesting aspect of the logistic regression is that due to the fact that it always goes from 0 to 1, we can extrapolate the model to where we don't have data, which of course is an extrapolation. So one can say, oh, well, you don't have the data there. How do you trust this data? Well, one of the good aspects of doing statistical modeling is that we have a way to estimate confidence intervals more reliably. So we have an extrapolation, but with confidence intervals based on the part that we have data. And so here I'm showing on the left the results for Coma, and on the right the later results that we did for Abel 35T8 and Abel 1736 in the Shapley Supercluster. So now looking to the meat and potatoes of our work is to compare our nucleation fraction for these environments with all the other environments where nucleation data were available in the literature at the time. So this work from 2021, this was our main plot. We plotted here the Coma nucleation fraction compared to the Fornax and Virgo clusters. And also we divided a local volume sample into galaxies groups that had an early type galaxy at the center and groups that had a late type galaxy at the center. So two things are readily noticeable in this plot. First is the fact that for all environments considered, the nucleation fraction is clearly proportional to the luminosity of the galaxy, in a way that for low luminosities or low mass, the nucleation becomes almost negligible around 10 to the 10, 10 to the 11, minus 10 to the, no, not 10 to the, sorry, minus 10 or minus 11 absolute magnitudes, sorry. And this is something that is very well known in the literature and is credited to the fact that the GC in spiral scenario that I showed in the beginning is dominant at low mass to the point that we almost no see the part of young populations in those nuclear star clusters. And with this, we join this to the fact that low mass galaxies might never form enough massive GCs or form GCs only at large radii because from the time that the GC starts to spiral towards the center of the galaxy, it needs to be massive enough to not dissipate in this path, or do not take so much time to reach the center that we don't see it today as a nuclear star cluster. It takes more than the time of the universe exists to go to the center of the galaxy, which is something that might happen if the galaxy is more elongated. So some GCs are formed on farther than others. But another thing that is obviously the most obvious thing is indeed Coma looked like had an increased nucleation fraction for a fixed galaxy luminosity larger than any other environments that we investigated. But even more, we color each of those lines by the estimated halo mass of each environment, and we can see that there seems to be an increase with the halo mass, with the nucleation, the probability of a galaxy to be nucleated for a fixed galaxy luminosity. We, at the time, theorized that this is something that is not predicted by the NSC formation models that I showed before. But one idea that we had is that in more massive environments, we have a faster mass assembly, especially in dwarf galaxies. And this might lead to more massive early GCs that might increase the likelihood of a nuclear star cluster to form within massive environments. But this is still a matter of research. And in 2024, we expanded this work then to the Shapley Supercluster. Now you see why Shapley was so interesting, because Shapley, by being the largest concentration of mass in the nearby universe, and the fact that we saw this correlation between the increased nucleation fraction with the estimated halo mass of the environment, Shapley looked like a perfect laboratory to study this kind of thing. What we saw in the end, I'm showing here the exact same environments that we saw before, although in this work we largely updated the local volume and Fornax samples with works that were released between 2021 and 2024. And in yellow and red, I'm showing the Abel 3558, which is the central Shapley cluster, and the Abel 1736A, the northwards cluster, respectively. What we see here is first that Abel 3558 indeed have a very high nucleation fraction, only comparable to the Coma cluster from the data that we had at the time. And this is something that may seem a bit weird, given that Shapley should be more massive than nearby cluster. But in fact, Abel 3558 itself has a very similar estimated halo mass to the Coma cluster, as I will show more explicitly in a bit. So this is exactly what we expected in this data. And in this part right here, it's a little bit smaller, a bit lower, the nucleation fraction from Coma, but we have to consider the uncertainties. But in the case of A1736, it was interesting how low it was, the nucleation fraction, comparing to galaxy clusters like Fornax and Virgo. However, if you put it in a plot with the local volume groups, it looks like to be more compatible with them when compared to the clusters. And it was very interesting because this is something that we did not expect at first. And another thing that I will briefly point out, but it's not something that was the main aspect of our work, but by using the updated local volume data, we were able to identify also that the division between early type hosts and late type hosts in the local volume created a difference in the nucleation fraction too. Like you can see now, we didn't see this much very clearly here. We already saw that the early type groups had increased nucleation to the late type central, but it was not very easy to see. However, oh, I'm coming back, sorry. Now it's much, much clearer that the early type hosts have a increased nucleation fraction than the late types. And in blue here, I'm showing an undivided local volume sample from another reference, Hoyer 2021, which also shows a similar nucleation to be more in the middle, but tends to the early types because there are more early type hosts, central galaxies in general than late type galaxies. But it's something interesting too that we don't go too deep, but it's another result that we was able to show. But the best way to see the influence of mass, of the estimated halo mass and the nucleation fraction is with this diagram. We develop an index, which is another advantage of using a model in contrast to just being the data, because we can extract a lot of information from the model itself. Like indexes calculate a lot of, we can simply put the magnitude and get an estimated probability for the nucleation, for instance. And we estimate this index, which is basically the magnitude at which a galaxy in a given environment have a 50% probability of being nucleated. So we get this index for every environment that we studied and put in a diagram with the estimated halo mass on the x-axis. And we can model a linear relation between this data in order to see very clearly that the more massive environments have a higher probability of forming, presenting galaxies with nuclear star clusters in general. And another thing that this diagram was interesting is because in this work, unfortunately, for A1736A, we didn't have the estimated halo mass for this subcomponent of the cluster. In the literature, we only had the estimated halo mass for the whole A1736 cluster. So we knew for a fact that this estimated halo mass was an overestimation of for this environment. However, we can use this model for estimated using all the other points to estimate what would be the halo mass of this object, a raw estimation, what would be the halo mass based on NSC occupation fraction. And the result was that this environment would be located exactly within the local volume environments. And we can estimate, of course, the uncertainty is very large. I'm not saying in any way, shape, or form that this replaces any other way to measure estimated halo mass. But at a point in the future where we would have many different environments here and more certainty about the relation between those objects, this might be an interesting way to have at least a rough estimation of halo masses for galaxy clusters based on the nucleation of the galaxies. So basically now I'll finish the presentation with my conclusions and perspective. The first thing that was interesting by this work is the consequence that it had in the small niche literature, which is studying extragalactic nuclear star clusters, because we studied the role of environment in NSC formation growth, that if you remember in the beginning of the presentation is not something that is readily predictable by the common formation scenario. Espera um pouquinho. Tá. So getting back after the brief interruption. So as I was saying, where am I mouse? Here. So I wanted to emphasize this work by Su et al. In 2022 that also looked into the environment influence of nuclear star cluster, but specifically within the Fornax cluster. And he compared the nucleation fraction between the Fornax main cluster and the Fornax A group that is falling to Fornax. And he found also an increased nucleation between the main massive cluster and the group that is falling. But another thing that he did that he can do because of the more localized data is to do a comparison of the nucleation with the projected distance within the environment. So here we have on the x-axis the distance to the center of the environment, the center of the Fornax cluster in megaparsecs. So this is another kind of study that would be very interesting for we to do if we had data enough for that. But of course, for things like Shapley that is too far away, still cannot do this at large radii. We only have normally the very center of the clusters. But you can see here that there is an indicative of a larger nucleation fraction closer to the center of environments compared to the outer region. However, after some radii, it becomes more or less debatable if there is a direct, to be linear or not, this relation. But at the center, yes, it seemed to be increased compared to the outskirts. It's another thing that can be studied in regards to environment in this subject. So another result that we had in our work, but it would be good to be even more in the future, is to add more environments with nucleation data. First, to increase the amount of points that we can do in a plot like this. We already added to the literature data for Coma, Abel 3558 and Abel 1736A. And we have data coming probably this year with a new environment that will be published that I can't say yet, that will be done with Euclid data. Euclid is a recent telescope that was launched that as well as the Vera Rubin Observatory, NSC, has the property of being large field of views with very deep photometry that are perfect to detect nuclear star clusters in nearby galaxy clusters. So we expect in the future to be this is something that to be more environments for us to put in a plot like this. These telescopes also make it much easier to detect low surface brightness galaxies as the ones that we want to detect. So another thing that is very important is that this motivates theoretical works to look into the environment relation of in the NSC formation and growth. And Lema et al. In 2021 used simulations with specific initial conditions related to the size and the shape of dwarf galaxies in different environments to reproduce this famous Sanchez-Janssen in 2019. But this is still a work in progress. This doesn't cover some of his ideas doesn't match very well the other results from environments that were released after him. But this is something very interesting that to be released also in the future. Also, another thing that I think is very nice is the fact that we employed statistical techniques that are common everywhere in data sciences, except for astronomy, because like it may seem a little bit left field to use logistic regression and everything, but this is something that is very easily accessible today with the programming languages that we use in astronomy, such as Python or R. So this is something also that papers after our first paper decided to use, because saw some of the advantages of this methodology. And this is it. I want to thank you for your attention. And finally, remember again to check our paper that was just released early this month. And the fact is that there are a lot of things that I didn't talk here due to time constraints, such as how exactly do we do all the math for the methodology, for the statistical methodology, all of the part of galaxy detection, how do we confirm that the objects are what we think they are, and some of the more contextual introduction to the field and everything. But that's it. Thank you.
Questions?
Very interesting work. Congratulations. How reliable is your estimate of the fraction of nucleated galaxies at low magnitudes? What I mean, these objects, as you have shown, are found in the center of the clusters, where interactions are dominant, and so it is very plausible that many dwarfs lose their outskirts, and what remains as the nucleus would be confounded with a globular cluster. That's why I'm insisting in this point, because it is in the central regions where most of these effects are stronger, is where those galaxies are found.
I want to go back a little bit, because this is one of the reasons why we... Oh, too much. This is one of the reasons that we select this range of absolute magnitudes here, because in fact we detect objects fainter than these magnitudes, but we not go too faint exactly to not go to objects that we are very hard to say whether or not they are a galaxy around a nuclear star cluster or some noise around the globular cluster, as you say. So it's unreliable to go to very low luminosities. But the way that we can do to avoid being so much unreliable is actually to go a little bit, to only probe a range that is not so faint and not so bright. That's mainly the idea.
Just to understand better the meaning of the faint magnitudes, what would be the magnitude, say, of Omega Centauri or 47 Tucana in I? Do you know?
I don't know.
-8. So you are in a region where you are unable to distinguish between galaxies and the globular clusters unless you are able to see the outskirts of the galaxy.
One thing that, at least for us, seemed to make it more reliable is the fact that we do the Cal-fit modeling of all the galaxies. And with the modeling, because like this, first we do a visual inspection of the detections. If it was basically only the visual detection, it was one thing. But as after we do the Gauss fit modeling, on top of the visual detection, have a two-pass filter let's put to our detections to see if those objects are really galaxies. Because, as I said, I should have put this plot here. Now I see this. But when we compare the sizes and the luminosities of our detected objects with regular dwarf galaxies in other environments, that we put this in a plot, that we put this in the paper, let's say that we have a very faint galaxy that we model with Gauss fit and we have the model, but this is not really a galaxy. Most likely, the physical properties that the model would show us would be very far from what is actually a galaxy at that fainter magnitudes. It will look more like imagine if you try to fit a noise and not a real galaxy. To not look like a galaxy, most likely. To be too large or be something will be weird. So by looking to this plot with the radius and the surface brightness, because it's independent of the distance, we can be more sure that they are actually galaxies up until that magnitude that we are selecting.
More questions?
Do you have an estimate of the masses of these clusters, and how does that mass of a cluster compares to the bulge mass? Is there any similarity to the Magorian relation with black hole mass and bulge mass?
Well, the black holes is something interesting that people always ask me when I'm showing this presentation, because, and unfortunately, just saying about black holes before I ask the rest of the question, the fact is that we are not very sure how do the black holes formation is related to NSC growth, because we don't know very much about how supermassive black holes are formed. But like in this work, we didn't have mass estimation because we only had a single band for each image. However, comparing to we have an estimation that like the peak of our from the behavior of the nucleation fraction, we would say that the peak is has a peak of nucleation around 10 to the 9. So if you look at our data here, this may be a good. So it would be at around -18 in absolute magnitude. It would be more or less what we see. However, this is something that the peak to be at 10 to the 9 solar masses is debatable. In NSC works, it's just that work that we have to base this, but it's basically the best that we can do to compare the two to get this mass in this context. I don't know if it answers.
Okay, because if I remember correctly, the black hole mass are about 1%, maybe 0.5% of the bulge mass. So
Yeah.
here, compared to the mass of the whole galaxy, it would be like 10 to the 7, because the peak is at 10 to the 9. So
Yeah,
to the nuclear clusters would have that 1% would correspond to 10 to the 7, which is
it's a lot.
it's just an order.
Yeah. Well, I think that maybe shields me from the black hole stuff on the subjects is the fact that we are looking at dwarf galaxies. So normally they're not expected to have a very massive black hole at the center. However,
that on those low masses, you do not get to form a black hole, but maybe a nuclear star cluster.
Yeah.
God knows, maybe.
No, there are several works in the literature that deal with this subject, but they are very tentative to make the connection between the nuclear star cluster. Like in the Milky Way, you have the nuclear star cluster and the black hole at the center. The most of the studies that I see with the connection between the two are on the Milky Way cluster itself. So it's something to look at.
More questions? No? Thank you.
Thank you.